hope you are all well and healthy and ready to learn the new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education, a research center Navsari in Civil Engineering Department. I am going to teach you the subject is design of reinforced concrete structures. In this subject, we are going to learn design of water tank. So in the previous lecture, we covered on the ground water tank as well as underground water tank, and in the underground water tank we covered rectangular water tank and circular water tank. But in a circular water tank we complete only sliding base water tank, means flexible base water tank. So in this lecture we are going to learn rigid base water tank. Example design of circular water tank fixed at a base and from the following data: inter diameter 12 meter, height 5 meter, gamma 80, gamma W 10 and phi 30, and use M30 grade of concrete and Fe 415 grade of steel. So tank shall be designed for the two conditions here. So first condition, assume a water tank is empty and soil pressure outside. And the second condition, water tank is full of water and no earth pressure from outside. So assume thickness of wall. In this case we assume a thickness of wall which is 400 mm. We assume this. We assume thickness of wall is 400 mm and external diameter of base is 12.8. Here we have all the data of the water tank, right? Internal diameter we have a height 5 meter. Let's change it back to here. Height 5 meter, gamma 80, gamma W 10. Now first of all we have to calculate step 1, condition 1, KA. We calculate KA is 1/3 and PA, equation KA gamma dash into capital H plus gamma W into capital H. And by this PA we found the pressure at a base is 63.33 kilonewton per meter square, and by this pressure at a base we can calculate compression force, hoop compression, PA into D by 2. So as well as hoop compression is 405.31 kilonewton per meter length. Now we are going to calculate maximum compressor stress in a concrete from the IS 3370 part 2 2009 table number 2. Sigma Cc is 8. So by this equation we found sigma Cc is 1, which is less than 8. So a thickness 400 mm is safe. Thickness 400 mm is safe. Now we are going for the calculate condition 2. The thickness of wall shall be followed from the top. Here you can see 800 mm at the top, 0.41 to 0.7 meter, 350, 0.7 to H is equal to 400. Means we have provided changing in the thickness. 400 at a base and top is 300 mm. Right? Now we have to calculate the moment. We are going to use IS table for calculating a moment. Just remember the equation. Let's check how to find out this moment. So here is IS 3370 part 4 1967 table number 9. Here is equation for the tension coefficient into gamma into H into capital R. First of all we have to calculate S square into D by 2. In the example we calculated it, right? Here is a S square into D by 2 is 5.21. 5.21. So here is a H is equal to 5 and 6. So we have to follow this row. And for the point 0h we can find a coefficient is 0.25. For the 0.1h, found coefficient is 1.3, as well as for the 0.9, we have to calculate all the coefficient here by the interpolation. By the interpolation, we can calculate a we find out a coefficient which is called k1. Okay, 0.0h here, 0.1h here, 0.2h here, and I make all the table here. Okay, this is the k1. Now we are going to design for this hoop tension. So provide hoop tension in typical calculation. Hoop tension is k1 gamma w into capital H into d by 2. So k1 into 10 into 5 into 12 by 2. So 3000 k1, 3000 k1. Now we are going to calculate k1 for the 0.5h. For the 0.5h, 0.5h k1 is 0.431. So hoop tension is 300 into 0.483. So 114.90 k1. 114.90 k1. Now hoop steel. Hoop steel is equal to T divided by sigma st. Same equation. So we can find out the hoop steel. Thickness 350 mm. Provide PT 0.24. So 115 mm. So hoop steel required. For the 2 zone 0.5h, 0.24%, so 840 mm square. For the 2 zone faces 420 mm square. So provided 12 mm dia at 200 mm on the both faces. Okay, here is a 420 mm square is a minimum. Here is a minimum, but we require 115 mm square. So we design for the 115 mm square, right? Now we are going to calculate tensile stresses in a concrete. Sigma CT is 1.5 m. So sigma CT, there is the equation I discussed. What is AG, what is AST. So by this we can find out the CT, which is 0.41, 0.403, which is less than 1.5. 1.5 we find from the IS 456 2000, right? Sigma CT, sigma CBC, M. So here is a design is a safe. Now here is I give the table for the all other calculation. All other calculation, depth, value of K1, hoop tension, hoop steel, thickness, and here is a hoop tensile reinforcement is given. Here is a design of the all other reinforcement, and here is a tensile stress calculation. Now we are going to find out K2. K2 from where? From table number 10, IS 3370, part 4. For the bending moment, S square d by 2 is 5.21. Let's check this. Table 10, here is equation moment coefficient into gamma h cube. S square by dt value is 5.21. So we can find all the data from this row. We can find all the data from this row. 0.1h, 0.2h, 1h, right? And these are the coefficient. So we can use this coefficient. You can see I made a table here. Plus and minus sign is important. Don't forget the minus sign. Then after we can calculate a bending moment K2 gamma W into h cube. So for the at the base h is equal to 1. So moment we find it. Okay. Then after there is a tension moment. So by the moment m upon bd square is equal to 0.358. 0.358. So D is equal to, so provide D is equal to 400 mm. These are the check. These are the check. So our design is safe. P by D is 90, so design is safe. So we have to calculate the design constant. You can remember all the design constant here. These are the design constant. Now D is equal to 300 mm, AST minimum 0.24%, so 960 mm square is the minimum reinforcement required. So we provide 12 mm dia at 100 mm liquid phase in a vertical direction, 1028 mm square. Here is a table for the depth point H, value of K2, BM, reinforcement provided. Here is a liquid phase, provide 12 mm diet, 100 mm center of center, and on the remote phase throughout the height same, right? So our design is completed. Now we have to calculate maximum shear at a base. Maximum shear at a base. So we have equation V is equal to K3 gamma WH. Shear coefficient, we need a K3 value from the table number 11. Let's 11 shear at a base of a cylindrical wall. Shear is a different coefficient, but here is the equation is for the triangle different, for the rectangular. Moment at a base is different equations. Okay. Triangular load fixed base and triangular rectangular load on the hinge base, and moment at edges. Our h square by dt value is 5.12. So by this row we can find out K3 value. We can find out K3 value. We have a triangular load, so K3 value is K3 value is 0.223, 0.197209. So we find out 52.25. So tau well equation is V upon BJD. So here is 1000, J is 0.861, 350 is the thickness, so 0.173 Newton per mm square, which is less than 0.22 Newton per mm square. So our thickness is safe. So our design is safe for this year. So at base P is equal to 0.24%, so tau C is equal to 22. So design a base slab. We have to calculate design a base slab. For the design a base slab, we provide 0.24% steel for the 150 mm thickness. So provide AST is 0.24 divided by 1000 to 75, so 180 mm square. So our design is completed. You can see here is for the 1 meter 10 mm dia, for the 1 meter 12. The height will be changed, the value will be changed. Okay. For the 0.5 different, we calculate the different loads and different coefficient for the different design. So our design is completed. Now our design is completed. So in the previous lecture we will cover elevated water tank, right? Here elevated water tank, rectangular water tank to design, approximate method, IS code method, circular water tank, intense tank. Okay, so we will learn all these designs. Till then, goodbye, take care.